someone asked about the example Sanders did in class, finding the inverse function of f of x equal to x minus 1 over x. And so here is the general process, which we'll do here, and then we'll do another example as well. So first things first, you want to write it as y equal to x minus 1 over x. It's just easier to manipulate y than it is to manipulate f of x. Second thing, switch x and y. Right, we're interchanging the roles of the inputs and the outputs when you find an inverse function. Right, that's exactly what the inverse function does, is it changes the job of x and y. He talked about this a lot in his lecture notes. My kind of favorite example is something like, f of x equal to 2 to the x and f inverse of x equal to log base 2 of x. Right here, the input can be 3 and the output is 8. Here the input is 8 and the output is 3. Because 2 to the third is 8, log base 2 of 8 is 3. These functions are exactly designed to be inverses because they're designed to undo each other. So, same idea here. We're going to find the thing that undoes what this does. Switch x and y. So x equals y minus 1 over y. And then we're going to solve for y, which is not always easy. My usual plan of attack if I have a fraction is to not have a fraction. I'm going to multiply everything by y. So x times y equals y minus 1. Then I'm going to try and solve for y, which usually means bringing all the things that have y's to the same side. Usually I bring the y's to the left because I like having a positive, so I'm going to make it y's to the right. So add 1 to both sides to get 1 over here. Subtract xy from both sides to get y minus xy over there. And then it's really, really key that on the side that has all the y's, you factor out the y. So I get a y, 1 equal to y. I'm going to factor out the y I'm left with. Let me erase this over here, it's kind of in the way. Y divided by y is 1, xy divided by y is just x. Finally, we solve for y by dividing both sides by whatever is over there. So I would say the last step is to rewrite this as f inverse of x is equal to 1 over 1 minus x. A couple things to note. These functions do undo each other. If I plug in something for f of x, like if I said, what's f of, I don't know, let's do 3. F of 3 is going to be, 3 minus 1 is 2 over 3, 2/3. The inverse function should take whatever you got for the output and spit back out the input. So it should be true that f inverse of 2/3 is 1 over 1 minus 2/3. 1 minus 2/3 is 1/3. And 1 divided by 1/3 is 1 times 3, which is 3. Oh yeah, it got me back to where I started. Inverse functions always do this. The other neat thing about inverse functions is their domain and range are interchanged. So here, this function has a domain that's x not equal to 0. I mean, the more nice way to say everything from minus infinity to 0, whatever. We're being a little bit lazy here. Here, the domain of this function is x not equal to 1. But if I look at this function, I can also see the range. The range here is y can't be 0. I can see that in two ways. People are being loud outside. I can see that either by noting that I have a fraction where the top can't be 0, so the whole thing can never be 0. But the more, gross, pat on my fingers, the more exact way of doing it is saying, oh look, the domain of the original function is the same as the range of the inverse function. We switched x and y, the x things here should correspond to the y things here. And more helpfully, it also means that the range here is everything except for y equal to 1. Y can't be 1. This will never be 1, right? X minus 1 over x, this fraction can never be 1 because the top will never be the same as the bottom. And for a fraction to be equal to 1, the top and the bottom have to be the same. So we can kind of use the inverse function, not just kind of, we can definitely use the inverse function to find the range of the original function, which is kind of cool. We can also show another thing which is true about these inverse functions, which is that if you compose them, right, if you look at f inverse of f of x, it's going to equal x. Right, I get f inverse of x minus 1 over x, which is, I'm going to plug into this function now, so it's 1 over 1 minus, sorry, instead of x, I'm going to put x minus 1 over x. Now, it should be noted here that 0 is not in the domain, right? The inner function is lacking 0, so this whole thing is lacking 0, even though when we simplify it, it's going to be just x. So multiply by x over x. The top is going to be x. The bottom is going to be x minus 1, which is going to be x over x minus x plus 1. The x's cancel, and you just get x over 1, which is x. So f inverse of f of x is equal to x, but it should be noted here that x can't be 0. Right? You couldn't do f of 0 because f of 0 doesn't exist, even though f inverse wouldn't do. Let's do another example, just because these are kind of good to do. Let's do actually an easier example, I think. So let's look at, say, like f of x equal to 2x plus 3 divided by 4. We're totally going to undo this. First thing, y equals 2x plus 3 over 4. Now this one's actually easy to undo because you can think of this as just kind of undoing the operations in reverse order. So this one, first you multiply by 2, then you add 3, and then you divide by 4. To undo it, we're going to multiply by 4, then subtract 3, then divide by 2, which is kind of great. But we don't have to actually think about that. We can just do the math. So now I'm going to solve for y. So multiply by 4. Whoops, that's an equals. Whoops, wow, that looks terrible. Subtract 3. Divide by 2. These functions exactly undo each other, and it seems pretty clear just by talking it out, but of course they have to undo each other. So f inverse of x is 4x minus 3 over 2. And whatever this does, that's going to undo it, and that's the hallmark of an inverse function. I think that's probably a good place to stop.